Good morning, friends. Time to begin the class. Reminder, we are having quiz 2 tomorrow, 10 o'clock, 1 hour duration, and the protocol is like before, exactly like before. All right. Um, okay, so in the last class, we were discussing the solution of the recurrence to the Catalan problem, right? So the main combinatorial ideas were presented in the last class, but I kind of hurried a bit through the mathematical jugglery, the last part of the last class. So, do I need to go through it once again, or is there any question, that specific question that some of you might want to ask, or should we kind of just move on from that point? Right, so the only trick we used was something called the generalized binomial theorem, which uses the generalized binomial coefficients. And everything else was just some mathematical jugglery, which I'm sure you have done in the past. That kind of jugglery, if not exactly that. Okay, so if there is nobody who specifically wants me to go over that once again, I can skip that and let's get into something called Ramsey theory today. So Ramsey theory is really a big theory. We are just going to peep into it and see quickly what we are able to see. Okay. Okay, so let me add a few slides quickly. Okay. Right. So yes, the plan is to look into Ramsey theory, and along the way, we will see rather two nice techniques. We'll add two tools into our arsenal. Okay. And I'll point them out as soon as we encounter them. Okay. So before looking at the main result that we are going to study today, I need to introduce handful of graph theoretic definitions, easy ones, but let me just put them down. Right, so definition. Yeah, so obviously we are, yeah, I hope it's clear that we are getting back into graphs, but then we are definitely not going to use the heavy duty graph theory that we studied earlier. So it's okay if you don't remember it. Although you should ideally remember it at this point of time because we are having the quiz tomorrow. Anyway, yeah, so let G equal to VE be a graph. A subset of vertices, subset S of vertices is called a clique. Okay, so I'm writing two definitions as a single statement. So respectively, independent set right? So I'm defining two terms, what is a clique and what is an independent set. Okay, so a subset of vertices is called a clique if every pair of vertices, distinct vertices, in S is adjacent, and it is called an independent set if every pair of distinct vertices in S is non-adjacent. Right, so every pair of vertices in a clique has an edge between them, and no pair of vertices in an independent set has an edge between them. Right, and the other graph theoretic definition which I want to use today is something called an induced subgraph. Let
Sir, excuse me.
yeah.
So, sir, it means that if V has a clique, then G must be a regular graph. Yeah, complete graph, sorry.
If V itself is a clique, then G is a complete graph. If V itself is an independent set, then G is the empty graph.
Okay, sir.
Yeah. Yeah. So yeah, corner cases, empty set. The empty set of vertices is always a clique, and it is also always an independent set. A singleton set of vertices containing a single vertex is a clique as well as it is an independent set by definition. Okay, so let's continue this other definition. Let G equal to VE be a graph. Okay, let G equal to VE and G prime equal to V prime E prime be graphs. G prime is said to be an induced subgraph of G if something happens. So what something happens? If you remember the definition of subgraph, right? So if I were to define a subgraph, what would I say? Right? Forget the induced part. Let's recall the definition of a subgraph. What is the criterion that G prime needs to satisfy to be a subgraph of G?
V and D, V prime and E prime should be subset of V and D.
Yeah, V prime should be a subset of V and E prime should be a subset of V, of E. Right, so now the definition is slightly going to change. So what we need is if V prime is a subset of V like before, and E prime is the set of all UV, right? So just look at this carefully. It is the set of all UV such that UV is an edge in E and UV are both in V prime. What is the difference? Right, so V prime is any subset of V, that is fine, that part stays the same, but E prime is kind of more restricted. So every edge which in the original graph G, which had both of its endpoints in V, is necessarily in the graph G prime also. Okay, so let us look at a quick example. Right, so suppose this is my graph. Right, let me call these vertices A, B, C, D. Right, and so then this right, so this is my G, this is a subgraph of G, but not an induced subgraph. Right, so the vertex set is a subset of the vertex set, the edge set is a subset of the edge set. So therefore this second graph is a subgraph of G. But why is it not an induced subgraph? Because, well, so the vertex set of this is ABC, and we have not taken all edges of the original graph whose endpoints are in the set ABC. In particular, we have missed out this edge. Right, so which is why this is not an induced subgraph. Right, so whereas something like this is an induced subgraph. Right. So is this definition clear? Any issues? Okay. Quick question. Let's see who can answer this. Okay. So suppose S is a clique in the graph G. Is S necessarily a clique in every subgraph of G which contains all of S, whose vertex set contains all of S? Right. So question. Right. So let me state it as two questions. Yeah, Abhinav, once again, let me just write it down and then I'll come to you. Yeah. So 2 questions and 1 question. Suppose G prime is a subgraph of G. G equal to VE. G prime equal to V prime E prime. S subset of V is a clique of G. What else? Right, and the other question is going to be respectively an independent set okay, and what else? So we and S is a subset of V prime, in fact, right? So is S necessarily a clique, respectively independent set of G prime? Yeah, somebody had an answer. Aniruddha, was it you?
So I think it was Abhinav, not me.
Abhinav. Okay, Abhinav, yes.
Sir, I think it's not always true.
Which question are you answering? I have stated, I have asked two questions.
Okay. Now this clique, it might not always be a clique.
Yeah. Yes. So answer in case of clique is no. What about independent set?
Yes, it should be.
Independent sets will be
Because
maintained, right?
since
Cliques
there
are
is
not maintained.
no edge. Yes.
Sorry?
Yes.
Yeah. Okay. Arin, yes.
Sir, I think the answer in both the cases should be yes.
No, I'm talking about subgraph, not induced subgraph.
Oh, I'm talking about induced subgraph. Yeah,
Ha.
in subgraph, clique should be no, and independent set should be yes.
Good. Yeah. So no for clique. Yes for independent set. Vedant, your hand was up.
The same answer.
Okay, good. All right. So, but yeah, fine. What we are interested in right now is induced subgraph. So, suppose I change the question and ask, suppose G is an induced. One sec.
Excuse
An
me.
induced
Okay.
subgraph over here. Now, what is the answer?
Both yes.
In both cases, yes.
Sir, I wanted to ask, I just forgot. Sir, is subgraph of a graph necessarily a graph?
Of course. What do you mean?
Okay. No, actually, I meant that here is an edge from CD. So would there be CD present on a vertex set of a subgraph ABC?
Oh, I see. Good point. Yeah. I am not sure what definition of subgraph I wrote. Maybe I need to rectify. Okay, fine. So let's do recall that once again. Okay, one sec. So I'll clean this up. So yes in this case, in case of a induced subgraph. Okay. Okay, recall. G prime is equal to V prime E prime is said to be a subgraph of okay. I think the way I said is, suppose G prime is equal to V prime is a graph, then it is said to be a subgraph if V prime is a subset of V and E prime is a subset of P.
Okay, sir. Thank you.
So then that makes sense, no? So I'll go back
Yes,
and
sir.
check what I wrote exactly in that slide, and if necessary, I'll fix it. Okay. So a graph, maybe I should put it this way. So a graph G prime equal to V prime E prime is said to be a subgraph of G equal to of a graph G equal to VE. If V prime is a subset of V and E prime is a subset of V. Right. Okay. So now, all right. So let's leave this, and now let us recall one problem which we solved in lecture 1. Okay. So if you recall, the problem I stated was, suppose you have 6 people, and every pair of them is a pair of are friends of each other, or they are enemies of each other. Then there must be either a subset of, or I should not say either. There must be a subset of 3 people who are mutually friends, or there must be a subset of 3 people who are mutually enemies. Right. So I hope everybody remembers that we have done this in the first lecture. And we also saw a next step of this problem in the tutorial, right? So where you want to guarantee that there is either a set of 4 people who are mutual friends, or there is a set of 3 people who are mutual enemies. Something like that I have given in the tutorial. I don't exactly remember the details, but yeah, something like that. How do you state this in terms of these definitions? The definition of a clique and an independent set. How will you restate that result? Right. So yeah. Okay, Divyanshu.
So like for that 6-1 in which we had 6 friends, so like we can say that there's a graph with 6 vertices, and then either it should have a clique of size 3 or independent set of size 3.
Independent set of size 3. Very nice. Okay. So recall. Right. So every graph on, let's say at least 6 vertices. Why just 6 vertices? You could have more vertices, right? So the proof works equally well. On at least 6 vertices has a clique of size 3 or an independent set of size 3. Right. So lecture 1, I guess. All right. So now our plan is to generalize this, right? Suppose I want to say that every graph of sufficiently large number of vertices has either a clique of size 100 or an independent set of size 1000. I want to make this kind of a claim. Is this a valid claim, right? So that is what we are going to explore. Okay. So can we say that question? Can we say that a graph with a sufficiently large vertex set, every graph sufficiently large vertex set has a clique of size, let's say 100. I'm just putting some arbitrary numbers over here, or an independent set size 1000. Any guess?
Yes, sir.
Who is it? I couldn't figure out who.
Raman.
Hello?
Ramanuj, sir. Wait, I'll get my head.
Ramanuj. Okay, yes, Ramanuj. Yeah, why do you think so?
Sir, this is the same problem as one of our first tutorial problems in which handshakes and no handshakes.
Yes, but I'm putting some arbitrary numbers over here. So you think that the result will generalize to an arbitrary numbers?
Yes, sir. I think we proved not proved. I think something similar was in the tutorial. You can create a recurrence in this, and from that you can say that it will generalize for every number.
What did we have had the recurrence already in the tutorial? I don't think so.
No, sir. I wrote it in the formula. I did it myself. And it was a weak upper bound. It was a weak upper
Sorry?
bound, not a strict upper bound for the recurrence.
That's fine. That's fine. Okay, so this is something you did yourself, and you figured out that this is the answer to this question is yes. Okay, fine. That's cool. That's cool. Okay, so we'll try to prove this. Okay. Well, so we'll try to quickly prove it because the proof essentially uses the same ideas, but then that will kind of motivate another problem, which is going to be the main focus of really of this class. Okay, so let us write down this theorem. For every k, l in natural numbers, there exists a number, let's call it n of kl, or okay, there exists a number n in capital N such that every graph which has at least n vertices has a clique of size L or of size K, or an independent set of size L. Okay, so raise your hand if you think you will be able to prove this by yourself. Let's see how many people are confident. Yeah, Ramanuj has already done that. Cool. Okay. Okay, fine. Fine. So not many people seem to be confident. So let us quickly do this. Right. So proof. Right. So we are going to use induction. Right. So by induction on. Right. So what I'll do is I'll leave a few blanks for you to figure out and fill up once you see the entire proof. By induction on what, and what should be the base case. Right. So I'll leave this for you to figure out. Okay. So let's consider an inductive case. Right. So let us, for the inductive case, let us assume that K is, I should say n union 0. Why not? Right. So for the inductive case, let us assume that K is greater than 0 and L is greater than 0. So obviously your whatever base case you state should cover the case where K is equal to 0 or L is equal to 0. And let me put it this way. Okay, so now what are we guaranteed by induction hypothesis? What does induction hypothesis tell us? Right. So the induction hypothesis, whatever you state over here, by induction on whatever you state over here, right? So that should ensure us that we can assume this as a part of inductive hypothesis. What can we assume? So there exist numbers n1, n2 such that every graph on n1 vertices has a clique of size K or an independent set of size L minus 1. Right, so every graph on at least n1 vertices has a clique of size K or an independent set of size L minus 1, and every graph on at least n2 vertices has a clique of size K minus 1 or an independent set of size L. All right, so whatever you state over here by induction, whatever thing you state over here, that should allow me to assume both of these claims as an inductive hypothesis. Okay, so figure out what exactly you should put over here. Okay, so now what? Now what? Right. So what do we do? Right. So the idea is the same as before. You isolate some vertex V. Right. Look at its neighbors. Either V has a lot of neighbors or V has a lot of non-neighbors. Right. So let me denote the non-neighbors by these kind of edges. Right. So this dotted blue edge really means, okay, that edge does not exist in the graph. Right. So now what happens? So now if I have if I can ensure that right, what should I ensure? So if I ensure that V has at least n1 non-neighbors, then what can we say? Then we can say that this graph, that the induced subgraph on these non-neighbors has an the induced subgraph on the non-neighbors has a clique of size k or an independent set of size L minus 1. So if this induced subgraph has a clique of size k, then we are done, because that clique in the induced subgraph is going to be a clique in the original graph. If the induced subgraph has an independent set of size L minus 1, I can add V to that independent set, right? Because V is not adjacent to anybody out of the subgraph, right? And that way I'll get an independent set of size L. And similarly, right, so this happens if the set of non-neighbors of V is greater than n1. Similarly, if the set of neighbors of V is greater than or equal to n2, if the number of neighbors of V is greater than or equal to n2, then what do we know? Then this graph, the graph induced on this set of neighbors, either has a clique of size k minus 1 or an independent set of size L by induction hypothesis. Right. So if it has a clique, if this graph has a clique of size k minus 1, we just add V to that clique and we get another clique of size k in the original graph. Right. And if this graph has an independent set of size L, then that's an independent set in the original graph, because we are talking about induced subgraphs over here. Right. So a clique in an induced subgraph is a clique in the original graph, and an independent set in an induced subgraph is an independent set in the original graph. Right. So let us I'm not going to write the complete proof, right? So I just gave you the idea. So let us kind of write it partially. Okay, so now what n should I choose as a function of n1 and n2? Anybody except Ramanuj. Aniruddha, yes.
Sir, I had a different doubt.
Okay, go on.
So without loss of generality, can we just prove it for a clique of size k, and then we can extend that and say that in the complement graph, where if two vertices have an edge between them, then they don't have an edge between them in the complement graph. There exists the independent set.
No, that's not what we are trying to prove, right? So look, how do you do it in this case, right? So I give you a graph which does not have a clique of size 100. What do you do now? So it's independent. It's a complementary graph does not have have an independent set of size 100. So what?
Okay, I get it. So we need to prove both using two indices n1 and n2.
Yeah. So you need those two indices essentially.
Okay.
Yeah, Vedant, your hand was up.
So I was thinking maybe we could do induction on L plus K.
L plus K, that is possible. Wait, but then you will have, okay, what is your base case in that case? What is your base case if you were to do an induction on L plus K? Are you taking K equal to L equal to 0 as the base case?
Yes, sir, I guess we could take that.
Yeah, but then if suppose you're working with the case where K is 0 but L is not 0, right? So then this argument is not going to work because you don't have this other, right? So if K is equal to 0 and L is greater than 0, you don't have this assumption, right? there exists a graph on n1, n2 vertices which has a clique of size k minus 1 or an independent set of size L, right? So that is a nonsense statement. Right, so I think a better way of stating the same thing is induction on k plus L is fine, but you should really take the base
K
case.
into L.
Yeah.
So maybe
Yeah,
we could say K into L is 0.
I couldn't catch that. What is
Sir,
0?
we could take K multiplied by L0.
K multiplied by what? I think the easier way out is just you just induct on the minimum of k and L. Right, so the base case will cover the cases where one of k and L is 0 or both of them are 0. Right, so the base case is k equal to 0 or L equal to 0, and then I'll leave this. Right, so it's a trivial statement actually. Yeah, so somebody's hand was up. I saw that hand, but I could not figure. I could not catch who was it. Yes, Somil.
I was just saying, like, it's fine to have multiple cases in the base case, right? Like, we could take the sum 0 as one case, and we could just like treat the case where one of k and L is 0, k
That
or
is
L
also
is 0 separately.
that is also acceptable. Makes sense.
Thank you.
Okay, so there is something here to be filled up, but although that is kind of trivial. Okay, so now my question is, depending on if I told you the values of n1 and n2, what value of n will you choose? So that something like this is guaranteed. Either V has a set of at least n1 non-neighbors, or V has a set of at least n2 neighbors. What n should I choose to ensure this? What is the smallest n should I choose to ensure this property? Yeah, Somil.
N1 plus N2.
N1 plus N2 is good enough. Yes, good. So, yeah, all right. So let n is equal to N1 plus N2. Let P be a vertex of G. Right. So, okay, such that every graph has something, right? So G be an arbitrary graph. I did not state that. Let G be an arbitrary graph with at least n vertices, right? Let V be any vertex of G. Yeah, so let V be any vertex of G. Now what? So now so therefore V either has at least n1 non-neighbors or at least n2 neighbors. Right, and then you continue. So so this is case, let's call this case 1. So let's quickly do case 1 over here, and I'll leave case 2 because it is analogous. Right, so let S be the set of these non-neighbors. Right, so we know that size of S is greater than or equal to n1. So by induction hypothesis, S has a clique of size K or an independent set of size L minus 1. Right, so so this, let's call this case 1.1, case 1.2. Right, so what happens in case 1.1? So we are actually done, right, because we have found a clique in the, right, so every clique in this subgraph is a clique in the original graph, and case 1.2, right? So add V to the independent set. Right, and then finish off case 2 analogously. Okay, any questions?
Sir, I did not understand. Sir, how is this induction on minimum of KL?
How is this induction on minimum of KL? So look what results am I, how is it an induction on minimum of KL? Oh, maybe I should, yeah. I understand, right? So you're trying to say that I am assuming the hypothesis for KL minus 1, and in case K is already greater than, K is already less than L. So this KL minus 1 will not be a part of induction hypothesis. Yeah, you're right. You're right. So maybe I should say induction on K plus L. Right. Now is it okay? So did I understand your concern? Sorry, who was it? I didn't see.
It was Viraj.
Yeah, Viraj, did I understand your concern?
Yes, I think it's clear.
Yeah. Cool. Okay. So now quickly let us define. Right. So let n of KL denote the, right. So what do we know? There exists some number n such that right, for every k and l, there exists some n such that every graph which has at least n vertices has some nice property, right? So let us denote the minimum such n by something, right? Denote the minimum n such that every graph with at least n vertices has a clique of size k or an independent set of size L. Right. So any easy bounds, inductive bounds on n of KL? Right. So what does this tell you? How can you relate n of KL with some other n of K prime L primes? Right. So what does this, what n did we choose, right? So this n1, right? N1 could perfectly have been n of K L minus 1, and n2 could have been n of K minus 1 L. And then Vedant, yes.
Yes, sir. N of k comma L minus 1 and n of k minus 1 comma L.
Yeah, tell the exact statement.
N of k comma L is equal to n of k comma L minus 1 plus n of k minus 1 comma L.
Does everybody agree? Any objections? I have an objection, but I would like somebody from the class to figure out an objection. Yes, Ramanuj.
So this is weak upper bound. It is not strict really. You can have a n which is smaller than this, but still satisfied that it has no k and
Correct.
L number of sets.
Correct. Yeah, you're right. Chinmay?
Yes, sir. Same. We just said that this can satisfy, but we don't know if it's the minimum number.
You don't know it's the minimum. So how should I fix this?
Less than equal to.
Less than or equal to. Okay. Right, so does everybody get a point why I cannot write an equal to over here? What I'm ensured is every graph with so many vertices has a clique of size k or an independent set of size l minus 1. Every graph with so many vertices has a clique of size k minus 1 and an independent set of size l. That implies that every graph with so many vertices has a clique of size k or an independent set of size l minus l. Right, but then the minimum number of vertices that are required for this property could very well be less than or equal to this. Okay, so this is just an upper bound. Right, is there anybody who in class who has not understood why I'm putting a less than or equal to over here and not an equal to? Yeah, okay, so now right, so now I leave this for you to verify. It's an easy thing, right? So claim, right? So if I were to replace this by an equality, this pretty much looks like a recurrence relation involving n choose k kind of things, right? So the claim that I'll leave for you to prove is n of kl is less than or equal to k plus l choose k, which is also the same as k plus l choose l. This is extremely easy claim. You should get this in less than a minute. Okay, so now this proves some upper bound on the number n of kl. Now the main focus of this lecture comes now. We now want to prove some kind of a lower bound on nkl. What does it mean to prove a lower bound on nkl? We want to prove that if the graph is not big enough, then it is possible to kind of systematically add edges in such a way that you avoid a clique of size k and you also avoid an independent set of size l. Okay, right? So okay, so what we'll just do, we'll just slightly simplify the problem. Henceforward, we'll just assume k is equal to l, and our goal is now going to be get a lower bound, get a good lower bound on n of kk. Right, so by the way, let us quickly also see what is an upper bound on n of kk. So n of kk is going to be less than or equal to 2k choose k, which is what? Which is less than or equal to any reasonable upper bound on this, which just involves a constant number of usual mathematical operations. What is an extremely trivial upper bound on
4
2k?
to the k divided 4 to the k divided by 2k plus 1.
What divided by what?
4 to the k divided by 2k plus 1.
Divided by 2k plus 1, and why?
This is binomial expansion, and 2 to the k choose k is the largest of these.
Absolutely, absolutely. So we know that 2k choose 0 plus 2k choose 1 plus blah 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 up to 2k choose 2k is equal to 2 to the power of 2k, which is same as 4 to the power k. Right, and we know that the middle guy is the maximum. Although we didn't prove this in class, I hope all of you know that the middle binomial coefficient is going to be the maximum, which is precisely this. Right, so the maximum is going to be, oh no, but no, hold on, that's a lower bound, no? That's a lower bound. I want an upper bound on 2k choose k. Right, so 2k choose k is going to be certainly greater than or equal to 4 to the k divided by 2k plus 1. That is fine, but I want an upper bound, so this doesn't seem valid to me. Right, but what I can certainly say is this let's be extremely crude about it. This is less than 4 to the k, 2 to the 2k. Right, because the sum of all these binomial coefficients is 4 to the 4 to the k. Is that okay? Right, so Who told 4 to the k by 2k plus 1? Was it you, Ramanuj?
So Rishabh.
No, sir. Rishabh. Huh?
Oh, Rishabh. Yeah. So Rishabh, is it clear that this is in fact a lower bound and not an upper bound?
Yeah.
Okay, cool. Cool. Right. So we want a good lower bound now. So we don't want an extremely trivial lower bound which says, okay, which we don't want a lower bound of the form, let's say k minus 1, right? So that's kind of trivial, right? So no graph with k minus 1 vertices can have a clique of size k, and neither can it have an independent set of size k. Right. So let's try to get a good lower bound on nkk. And the way we will get a lower bound is the following, right? So we'll say that let us look at the set of all graphs over some n many vertices, right? So right, I'm just giving an informal idea of the proof before I state the theorem, right? So let us fix some n, right, and let us fix some vertex set of size n. Okay, so this is the set of all graphs over vertex set V, right? So some of them are going to be bad graphs. So what is a bad graph? A bad graph is a graph in which which has a clique of size k, or it has an independent set of size k. Okay, right? So we want to prove that there exists at least one good graph. Okay, so now this set of bad graphs, right? The graphs which have at least which have a clique of size k or an independent set of size k, I'll decompose into several categories of bad graphs. Okay, so for some set S subset of V, right? So size of S is equal to k, right? So I'll denote this set. Let's call this set BS, right? So this is the set of bad graphs. This is the set of graphs in which S is either a clique or an independent set. Set of graphs where S is either a clique or an independent set. Okay, so is the definition of this set B S clear? B sub S clear? Okay, and now what do we want to prove? We want to look at all possible BSs, right? All possible sets of bad graphs, and then we want to prove that there exists something which is outside them. Okay, right? So the goal is to prove that there exists a graph on n vertices where n is some small enough number which does not have a clique of size k, which does not have an independent set of size k. One way you could have done perfectly fine is a proof by construction, but if you try that, it's going to be a big mess. I mean, it's going to proof by construction is a valid proof strategy in this case, but it's going to land you in a problem, right? It's not so easy, right? So we are getting around that problem, and we are designing another proof strategy to prove these kind of existential statements, right? So you have all these sets. For every set you have this set B, and you want to show that the size of the union of all these sets, right, is strictly less than the size of the whole set, which is the set of all graphs over the vertex set V. If you somehow prove that, then you're done, right? So if we prove that the union over S subset of V, size of S is equal to K of the set V sub S, right? The size of this union is strictly less than the number of graphs over the vertex set V. Okay, strictly less than, right? So then we can say that there exists a graph over V over n vertices that does not have a clique, a K clique, and does not have a K independent set. Yeah, Chinmay.
So like, could you please explain this this intuition again? I didn't get it. Like on like the regions that you were creating on the left.
The region.
The regions that you were creating on the left, like what do they denote? I didn't get it.
I'll explain that. Okay. So what is the motivation behind, right? So what do you want to prove? So you are given some small enough n, and your goal is to prove that there exists a graph on n vertices which does not have a clique of size k, and it does not have a clique independent set of size k either. What is the first proof strategy that will come into your mind? The first proof strategy is a proof by construction. You actually give a construction of such a graph, right? But if you try that for a largish kind of k, it's I mean, unless it's this n itself is like less than k, you are going to land up in problems, right? It's not so easy to construct explicitly such a graph. Right, so we are taking some kind of an indirect route to prove this existential statement. And what is that indirect route? We will just prove that, let us look at the set of bad graphs, right? What is a bad graph? A bad graph is a graph which has an independent set of size k or a clique of size k. And we'll prove that this is a strict subset of the set of all possible graphs on that vertex set. Once we do that, we are done. Right, so what we will do is we will classify all the bad graphs depending on where does the badness of that graph lie. It could lie in several places, so therefore a graph can be bad for several reasons. Okay, so now I am defining this set B sub S as follows, right? So S is, right, so for every S of subset of size V which has size k, for every S which is a subset of V and S has size k, I am defining this set B sub S. What is B sub S? B sub S is the set of graphs in which the set S, the set of vertices S, is a clique or it is an independent set. Okay. Now I know that every graph, every bad graph must belong to some B sub S. Right, and therefore my job is to prove that the size of the union of all these B sub S sets is strictly less than the total number of graphs over the vertex set V. Does that answer the question, Chinmay?
So like basically then what will happen, there will be some graph which is which has vertex set which has a vertex set subset of V which is a good graph, right?
Sorry, I couldn't catch that.
So like if we show this, then basically we are trying to show that from this bigger circle there is some graph which has vertices subset of V which is a good graph. So then that will be a lower bound.
Vertex set is exactly V, and that is a good graph. So which means your nkk must be strictly greater than this n, whatever n you have over here.
Okay.
Okay. Cool.
Yes, sir.
Yeah. Okay, nice. Right, and the way we will prove, right? So the way we will prove this kind of a result is using something called a union bound. It's an extremely trivial statement, but extremely useful. I mean, unbelievably useful statement, right? So what does the union bound say, right? So let me just state it in the next slide. So the union bound says, right? So let A1 through A whatever n be any collection of finite sets, right? So then the size of union of A1, A2, union AN is just less than or equal to the summation over I going from 1 through n size of AI. Extremely trivial statement, but extremely useful statement. Right? So I hope I don't need to prove this. Right? So this is the way we will use to prove that the size of this union is less than or equal to something, and then this itself will be less than the number of graphs over the vertex set V for whatever an appropriate n that we choose. And that will imply that the number nkk is actually is strictly more than n. Okay, so let us state this as a theorem. Okay. For every k, there exists a graph with, I'm intentionally leaving this as a blank. We'll derive this number and then we'll come back and fill it up over here, right? So with n equal to some number of vertices, which has neither a clique nor an independent set of size k. Right, so we are going to fill something in this blank, but we'll see the proof of this theorem and then we'll come back and fill the appropriate number over here. So we are really trying to derive the number and not tuning our proof to target a specific number. Okay, so proof. Okay, let V be a set of n vertices. Right, so the number of graphs over V is what? Come on, this is an easy kind of question. Should I ask a random student in the class? Chalo, Vaibhav. Anybody, come on. Is this so hard? Yeah, okay, so there are some people who have raised hands. Okay, chalo, Sachit. Sachit hasn't spoken today.
2 to the power n minus 1 by 2.
2 to the power n choose 2. Yeah, 2 to the power n times n minus 1 by 2. Good. Right, so the number of graphs over V is 2 to the power n choose 2, which is same as 2 to the power n times n minus 1 by 2. Right, so for every pair of vertices, every unordered set of two vertices, you have a choice of either making it an edge or not having it an edge. Right, so this is the number of graphs over V. So now let for every subset S of k vertices, let B sub S denote the set of graphs over V in which S is either a clique or an independent set. Right, so for every subset of k vertices, I am defining this set B sub S. Right, so now what is the size of B sub S?
Uh, 2 to the
2 to the power
NC2 minus KC2 into 2 plus 1.
Into 2. Okay. What is the justification? Why is this so?
So for every edge which is not part of the, oh, there's some extra edges. No,
Sorry?
nothing. So I'd say for every edge which is inside this, which is say consists of only this S vertices of S, you have them like their state fixed. They're either this subgraph which consists of only S, there are only two options. It's either a complete graph or it's an empty graph.
Okay.
And for every other vertex and for every other edge, it can either, and for every other, like, you can either have that edge in the graph or not.
Correct. Yeah. Divyanshu, your hand is up.
So like I was a bit confused regarding this BS and all that. So can you just give an example for small sizes? Like
Acha. Okay, fine. Yeah. Okay. So okay, example. Okay. Let's go to the next slide. Right. So let's take this graph. Right. So my vertex set is A, B, C, D, E. Right. And now let's say K is equal to 2. Now, if I take S is equal to, let's say, the set AB, right? So now this graph G, so then this graph G belongs to the set BS. Why? Because AB is a clique in B sub S, right? What other S does this graph G belong to? So G also belongs to the graph. G also belongs to the graph B sub, let's say, BDE. Why? Because BDE is an independent set of G. Although we have, right, so we have changed the value of K, but okay, let's get rid of this actually. Right, but G, for example, over here does not belong to the set B sub CDE, let's say. Why? Because the CDE is neither a clique nor an independent set. Right, so is this good enough an example?
yes, sir, fine.
Yeah. Right. So now, what is the size of the set B sub S? So as somebody argued, I forgot the name. Right. For every pair of vertices which contains exactly one vertex from the set S, you have a choice: either make it an edge or don't have it as an edge. Doesn't matter. Right. So that way you have so many choices. Right. How many pairs of vertices do you have? An unordered sets of 2 vertices do you have, in which at most one vertex is in S, right? So n choose 2, which is the set of all subsets of 2 vertices, minus k choose 2, which is the set of, which is the number of sets of 2 vertices, both of which are in K, right? So n choose 2 n choose 2 minus k choose 2 is the number of sets of 2 vertices having at most one vertex from S. Right, and for all such pair of vertices, or all such subsets of 2 vertices, we have a choice: either make it an edge or don't have it as an edge in our graph. Right, so the number of such graphs, that count will come out to be 2 to the power n choose 2 minus k choose 2. On top of that, we have a choice of making S either a clique or an independent set. Right, so which is why we have this 2. Is this okay? Any questions? Right, so the size of the set B sub S is this. So now by union bound, what do you have? By union bound, the size of union over S subset of V, size of S is equal to K, B sub S is less than or equal to the summation over S subset of V, size of S equal to K, size of the set B sub S. Right? So this is equal to, right? So for every such S, this size of B sub S is the same, and the number of such S's is n choose K times 2 to the n choose 2 minus K choose 2 times 2.
So I couldn't understand how we derived this expression. Could you explain again the cardinality of BS?
Sorry, cardinality of
BS.
BS. Yeah. Okay. So how did you have this? How did you have this? How did you derive the fact that the number of graphs is n2 to the n choose 2?
So first we find the number of vertices which can be formed of V set. That is n C2, number of pairs of vertices.
N2.
Yeah. And the graphs will be like any finite subset of the edge set. So
any finite subset of the edge set is a graph. Good.
Yes.
Now what do we want? We want a graph in which S is either a clique or an independent set. Okay?
Right.
But the same logic which you applied for every set of vertices which has one vertex in S and one vertex outside S, or both vertices are outside S, right? So for every such pair of vertices, we have a choice. Either we could make it an edge or we could not make it an edge. Exactly same logic. Okay?
Okay, sir.
Yeah, is that absolutely clear, Siddhant?
No, sir, I'm still thinking about it.
Right, so what did you have? So if you're just counting the number of graphs over the vertex set V, for every pair of vertices, right, you have a choice. Either you have this edge or you don't have this edge, right? Which is why you have this 2 to the power n choose 2. Right. Now the constraint is I want a specific set of vertices S as a clique or an independent set. That is what I want. Okay, so now again for every pair of vertices which is outside S, I still have a choice. Right, what is the constraint? S must be a clique or S must be an independent set. What happens outside S doesn't matter.
Right, sir.
Right, so for every pair of such vertices, both of which are outside S, I have a choice. For every pair of vertices such that one of them is in S, I still have a choice either to have this edge or not.
Right. Yes, sir.
Right, so that gives me 2 to the power n choose 2 minus k choose 2.
Okay, sir.
And then on top of this, I have a choice of making this either a clique or an independent
set. Okay.
And that gives me two choices.
Got it, sir. Thank you.
Good. Anybody else who is still confused? Okay, awesome. Right. And let me just upper bound this. Yeah. Okay, so let me just say this is less than or equal to. Let me pull out this 2 to the n choose 2 because I somehow want to kind of cancel out with this 2 to the n choose 2. So this is less than or equal to 2 to the n choose 2 times this n choose k is obviously upper bounded by n to the power k. Check that. Yeah, obviously there is a k factorial involved, but I'm ignoring that because it's only in the denominator. Right, so this is less than or equal to k to n to the k, and then what is left? So you are left with 2 to the power minus k choose 2. Right, 2 to the power minus of k choose 2 and into 2. Right. So now if I choose my n, if my n is such that this quantity is strictly less than 2 to the power n minus 1 by 2 or 2 to the power n choose 2, then I'm done. Right. So let us take this to the next slide.
Sir, can you repeat the last statement that you made?
So this is an upper bound on the number of bad graphs, right? Graphs which have either a clique of size k or an independent set of size k, right? So remember, this is a set of bad graphs, right? Every graph which is a clique of size k or which has an independent set of size k is going to belong to some B sub s, and therefore it is going to belong to this union. If we prove that the size of this union, which is upper bounded by this quantity, is strictly less than 2 to the power n choose 2. What does that mean? It means that there is a graph which lies actually outside this union.
Right, sir.
Yeah. Okay. So now we are going to choose our n in such a way that this quantity is going to be strictly less than this quantity, right? So that is what I'll write over here. So I think this is a good point of time to write it over here. Fill up this blank, right? So n is right. So there exists a graph with n equal to how many? What should I fill up over here? So let's the floor of 2 to the power k left. Okay, so 2 to the power k minus 1 by 2 minus 1 over k. Right. So now you'll soon realize where did this magic number come from. Right. So roughly exponential in k, roughly square root 2 to the power k. Right. Okay. So what do we have? So we have the number of bad graphs. Which have a k clique or a k independent set. So we proved that this is less than or equal to 2 to the power n choose 2 times what? N to the power k times what? 2 to the power minus k choose 2 times 2. So this is what we proved, right? And now what do we have? So now this quantity 2 to the power n choose 2 times n to the k times 2 to the power minus of k choose 2 times 2. This is strictly less than 2 to the power n choose 2. When does this happen? This happens if and only if, right? So this happens if and only if, let me cancel the 2 to the power n choose 2. What is left? N to the power k is strictly less than 2 to the power k choose 2 minus 1, right? So this I'm taking into the numerator, into the power, right? So this happens if and only if I'm just taking the kth root of both sides now. So this happens if and only if n to the n is strictly less than 2 to the power maybe I should have added a minus 1 over here. Okay, let's see. 2 to the power k choose 2. Okay, k choose 2, the kth, if I take the kth root of this, I'll just get k minus 1 by 2 in the exponent minus 1 over k. Right? With n, let me best, instead of making it equal to, let me just say n less than so many vertices. There exists a graph with, okay, let me state it this way, n equal to this minus 1, let's say, right? So that this n is strictly less than what we want it to be less than, right? So this is given to us, right? So the way we should really write is, this is given to us, therefore this holds and therefore this holds. Okay, so let me do it that way. what just happened? Okay, this is better. Right, and I'll just change it into an implication. So this is given to me, so therefore this happens, therefore this happens. Right, so therefore there exists a graph with n vertices which does not have a clique of size k and does not have an independent set of size k. Right, so which means corollary nkk is at least whatever that was, 2 to the k minus 1 divided by 2 minus 1 over k. Oh, I need to plug up my computer. Okay, any questions? Is there anything which is not clear, something which is partially clear, something which you would like me to explain once again?
Sir, can't we get a much better bound of n is less than or equal to kc2 minus 1 from this?
Less than or equal to what?
N is less than or equal to kc2 minus 1.
N is
Because
less than or equal to kc2 minus 1. We are not trying to get a bound on n. We are given a bound. We are given a bound on n, and from that we are trying to get a bound on the number of bad graphs.
no. So the thing is, we like badly approximated nck as n to the k.
Yeah. So what should you? What do you want me to do over there?
No. So the thing is, now we approximated it worse, and that gives us a better bound for some reason. So that's confusing. So see, if you go to the next slide and you have rather than having n to the k here, you let it be n ck.
Okay, so let me use a different color. N choose k. Then what?
Yeah. Then this is less than 2 to the n.
2 to the, what do you mean?
Like this will be less than 2 to the n, right?
Oh, n choose k. Acha. You're saying n choose k will be less than 2 to the n. Okay, fine. So then.
And
but
so
2 to the n is worse bound, right? 2 to the n is a worse bound than n choose k, no? As n to the power k, no? Right? So if your k is like some 100 or something, n to the power k
I see.
is,
Okay.
is better than 2 to the power n, no?
Yes. Right. Yeah, that was confusing.
Okay. Yeah. So what is Ramsey theory after all? Ramsey theory is just it just concerns proving these kind of statements, which say that if you have a large enough structure, then it must have one of these finitely many structures as it's sitting inside it as a substructure, right? So we saw a particular case of it where we proved that okay, the small structures which we are interested in is a k clique and an L independent set, right? And then we proved that if a graph is large enough, one of these must sit inside it, right? So this is all Ramsey theory is concerned about. This is one comment. The second comment, I could have restated or reproved this in a slightly different language. In what different language? Instead of saying that let us try to count the number of bad graphs, I could have put it in a different way as follows. Let us consider a uniformly random graph from this set of graphs over the vertex set V. Okay, how do you generate a uniformly random graph? For every unordered pair of vertices, you flip a coin and you decide whether that edge is in your graph or not. Okay, right? So I'm using probability over here. I'm defining some kind of a probability space on the set of graphs over the vertex set B. So then what I could have said is that, okay, so then I'll claim that the probability with which you get a bad graph, with which you get a graph which contains a clique of size k or an independent set of size k, we will plan to prove that this probability is strictly less than 1. What does that mean? Right? So if the probability of this bad event is strictly less than 1, there must be a graph in your probability space which is a good graph. Exactly the same idea, it's just that you're using a different language. It's just like writing the proof in Hindi instead of English, let's say. Okay, and the probabilistic version of the union bound which you would have used is the following. So union bound probabilistic version. So if E1 through En are events in the same sample space, then the probability of the union of these events, E1 union E2 union En, is less than or equal to the summation over I going from 1 through n, the probability of EI. Right? So instead of defining this set BS, we would have defined an event E sub S, which said that the set S is a clique or an independent set in the random graph that you choose. And then you would have found out the probability of ES, which would have been this expression except the n choose 2 term, 2 to the n choose 2 term, because that would be a part of the denominator. Right? And then you would just sum them up and you would prove that the sum is strictly less than 1. That's all. Okay, so is it clear the what kind of probabilistic proof I'm trying to prove? I'm trying to state. Right. So if you want to prove that certain object exists, what you do is somehow you define a random process and you prove that objects which don't satisfy the property you want them to satisfy occur with probability strictly less than 1. That's good enough. Okay, so I did not go into the details of this probabilistic version because we have not done probability in this class. I believe you are having a different course on probability. Okay, so that's it for today. So, but we have some time for questions. We have like 6 minutes for questions. Yes, Abhinav?
Sir, you said that something like it's like whatever we have to prove that its probability of occurring is strictly less than 1. But some right, that event can occur. I did not get that point.
Abhinav, your voice, I lost your voice, couldn't hear you in between. You'll have to repeat it. Yeah, Abhinav? Abhinav, please repeat your question or send it on chat. Chinmay?
So like, could you repeat like what was E1 here?
Okay.
Or, like,
so
was it related to the R case or like is it a generalization?
Sorry?
Like, did E1 have something to do with this BS or was it like just a general statement?
It had. So this is the cardinality version of union bound. Analogously, we have the probabilistic version of union bound. And all I said was there is another way to write this proof in a slightly different language, where instead of defining the set B sub S, you define the event E sub S, which says that S is a clique or an independent set. Independent set in the random graph that you generate, in the random graph generated.
So like basically probability of S being a clique in the entire space of all graphs over V, right?
Exactly. That is what you will get over here, and that right. So that probability will just be 2 to the power n choose 2 minus. Sorry, what will that probability be? It will just be 2 to the power minus k choose 2 times 2. Right?
Okay. Got
Yeah,
it.
because you will divide this cardinality by 2 to the power n choose 2, and that will give you the probability. Okay, and then when you take the union bound, you will just sum up these probabilities, and the upper bound on the resulting probability will be n to the power k times 2 to the power minus k choose 2 times 2. Now, if you prove that this quantity is less than 1, then you are done. Sorry?
Like we were finding, we are trying to find the total number of graphs over V which have a clique or independent set. There we are finding the probability of that.
Probability, right? Exactly. Which is why I said you are just using a different language. Instead of English, you are using Hindi. That's all. Instead of using cardinality, you are using probability. Okay?
Yes, sir.
All right. Anything else? We still have 3 minutes.
Sir.
Yeah, Shibashish.
Sir, in this slide, could you just explain the part after n is less than 2 to the power k minus 1 by 2 minus 1 by k after that part? What you have done?
Yeah, all that is just mathematical manipulation. I'm just taking the raising both sides to the power k, right? And then noting that k times k minus 1 by 2 is k choose 2. And then I'm just doing what? I'm just multiplying. I'm just adjusting the terms, right? I'm just multiplying both sides by 2 to the n choose 2. I took this 2 to the k choose 2 minus 1 term to the left hand side. That's it.
So I didn't get that how we concluded that from this that nkk is means how a graph with n vertices does not have a clique.
Okay. So what did we prove? We proved that every graph which has strictly less than these many vertices, or sorry, we proved that there exists a graph whose number of vertices is strictly less than this. Right? Sorry. What did we prove? We proved the graph. We proved that over so many vertices, 2 to the k minus 1 by 2 minus 1 over k, let's take the floor of it minus 1, there exists a graph in which you neither have a k clique nor do you have a k independent set. But now this nkk is a number which ensures that if your number of vertices is more than this, then you necessarily have a clique of size k, or you necessarily have a independent set of size k.
Okay, sir.
Right? So therefore, if you chose your nkk, if nkk were to be less than this quantity, then that this one graph that you could manage to prove the existence of would be a counter example to your claim that, right, to your claim that nkk is the minimum number for which guarantees that every graph which is strictly larger than that, which is larger than that, has a k clique or a k independent set. Siddhant?
Sir, in the proof of the theorem which we said at least n vertices which has clique of size k or independent size l. So I couldn't understand how it was an induction on k plus l.
How was it an induction on k plus l? What did we assume? Right. So we wanted to prove the claim for a specific k and l. As induction hypothesis, we assumed that the claim is true for all k prime l prime whose sum is strictly less than k plus l. And which is why we are assumed that the claim is true for k l minus 1, and we are allowed to assume that the claim is true for k minus 1 l. Right? So claim true for all k prime l prime such that k prime plus l prime is strictly less than k plus l. Right? So therefore the claim is true for these two pairs also. Okay?
Yes.
Sir. All right. Time is up. We are meeting in the evening for the tutorial. So see you then. Yeah, by the way, people were getting desperate about the quiz and so on. So today itself, I'll try my best to release the answers and the marks, and I'll also try to add a few problems to the tutorial. Okay, although that is not so urgent, but yeah, quiz and homework. Homework will not be able to release, homework 2, but quiz 1 and quiz 1 solutions, marks, and homework 2 solutions. We'll try to release by today. All right, chalo. So see you in the evening. Siddhant, your hand is still up?
No, sir. Sorry.